Welcome everyone to Module 5, the first part of Module 5 of the massive online course of Breach Black Sea project. In this module, we'll be talking about smart sensing in the context of Black Sea oceanography. So I'm a chemical oceanographer. I'm Mustafa Yücel. I'm professor of oceanography in METU Institute of Marine Sciences. I'm one of the leaders of the relevant work package of our project, also taking part as co-coordinator of the project. So today, actually, I'll start with a broad overview of why we need in situ sensing and the so-called smart monitoring of multiple stresses that are acting on the Black Sea ecosystem. And then we'll cover basic principles of in situ sensing, and then I will demonstrate some of the recent technologies used in especially deep water chemical sensing. Then briefly in the final part of my presentation, I'll try to feature some aspects of how Breach Black Sea advanced certain technologies throughout the project and the legacy that's left behind after the project. So many of us are familiar with how the world looks like from space, and thanks to satellite technology, now we can see the Earth's surface in different colors. Temperature, salinity, sea surface height, atmospheric composition, many different parameters can be now mapped in real time by satellites, and then they are available mostly online. But this creates a sort of two-dimensional image of the Earth, but especially the oceans are three-dimensional in nature. The deepest part of our oceans is around 11,000 meters deep, and the average depth of the oceans is almost 4 kilometers, and satellites can only see uppermost meter of our oceans. So much of the interior of the ocean, the majority actually of our oceans cannot be remotely sensed. We need technologies working inside the ocean to monitor the health of the ocean. Why do we care about oceans? Of course, I think you will be hearing more about that also in other modules of this massive online course. But currently, ocean interiors, especially the deep ocean, is very much under-observed due to challenging conditions such as darkness, high pressure, salt content. But understanding the interior deep oceans is very vital to understand elemental cycles, the habitat nature, storage of carbon, recycling of pollutants, many other things. So in the context of digital twins also, we need real-time and continuous data feeds to be able to represent our oceans as accurate as possible. Black Sea is also a very deep environment. Its deepest part is almost 2,200 meters deep. And you need underwater tools capable of the specific Black Sea conditions. Again, I'm sure this was touched upon in different modules, but Black Sea is unique in the sense that much of its volume is oxygen-free and contains toxic hydrogen sulfide gas. So you need underwater tools, new tools capable of withstanding these conditions. So challenges of in situ sensing, smart monitoring in the Black Sea is the same, actually, as challenges related to general ocean observations. In oceans, we are dealing with a huge actual range of scales and processes occurring at a huge range of temporal scale and spatial scale. For example, molecular processes or plankton movement occurs maybe in millimeter to centimeter spatial scale. But when you think about gyre circulation or mesoscale phenomena, they occur over tens or even hundreds of kilometers, taking years. So that's the challenge of temporal scale and spatial scale. Another scale issue comes with when you want to observe the dynamic nature of natural systems. On the left, for example, you see a nitrate concentration from a coastal location. In the bottom panel left, you see discrete bottle samples taken weekly and then in a 3-day interval. So the black circles, black diamonds represent weekly sampling. You see even in weekly sampling, which is very hard to do in most marine waters, you miss many of the phenomena, and then when you increase your sampling interval, you start to capture some short-term phenomena. And then when you deploy a sensor, as you see in the upper panel, then you even see hourly or dynamic conditions that occur that last only a few hours, and then they retreat. So thinking about, for example, a nitrate flux from a coastal location, from a river to the coastal ocean, it's actually much of the flux occurs through these sort of episodic fluxes. So your sampling interval is very important, and in order to maximize it, you need to use sensors. Another example is from pH, again from different coastal locations across the world. On the x-axis, you see day, monthly observations from different locations, and on the y-axis, you see pH value. Open ocean pH, as you see in the panel A, it's mostly constant, but as you approach to coastal locations, dynamic conditions increase. Even if you're around the carbon dioxide vent in a coastal geothermal setting, then the pH fluctuations will maximize. So it's almost impossible to capture these sort of dynamics with discrete chemical measurements, no matter how your measurement is sensitive. Back in the lab, no matter how clean your sampling is, you need in situ tools capable of resolving these dynamic conditions. We talked about undersampling. Another example is from this hypothetical chlorophyll survey, which you see on the right. When you display an area in 6 samples, you will get basically 6 data points. But on the lower right, you see a real distribution from a satellite. Of course, satellites need to be calibrated. They need to be validated with real data as much as possible. But no matter how many samples you collect, you will never actually present the real variability. So yeah, we talked about variability in space and variability in time. Another important concept when thinking about measurements, any measurements actually, is precision and accuracy. I think it's important also to review these concepts before we discuss any specific technology. Here, the analogy with archery is quite useful. On the left, for example, you see different shots with an arrow. You can also think of them as individual measurements and imagine that yellow dot is the true value. And here on the very left, you see some shots around the yellow area. They are somewhat accurate, but they are accurate, but they kind of revolve around the target, which means that they are not precise. The measurement, they are not precise. The repeatability of the measurement is not good. So it's somewhat accurate, but very, very low in precision. The middle panel shows you a precise but very inaccurate measurement or archery shot. The shots are very close to each other. The measurements replication is very good. You repeat your measurement, but it's constantly there's a certain distance to value. It means it's your measurement is precise, but your measurement is inaccurate. So and on the very right, you finally hit the target with all of your shots, and your measurements are both precise and accurate. So you want that actually in the measurement you are making. So some other concepts: detection limit. A detection limit is the smallest amount of analyte that can meaningfully determine any technology, any measurement technology, laboratory or in situ or sensor, your eyes, any detection organ or technology do have detection limit. So there's only a certain level of signal you can detect with your detector, and then you can meaningfully process it. And your detected signal should be meaningfully above a certain noise level to be able to consider it as a real measurement. And there are various ways of calculating the noise or signal to noise ratio. Sometimes people use 2 times the baseline, or sometimes 3 times. But no matter which statistical approach you use, you need to be considering noise, the fluctuation, which is actually the precision of your measurement technology. You need to be sure that when you detect something, that's actually a real value. Detection limit is important. So with all these in mind, the idea of a sensor, especially biogeochemical sensor, is that there's a certain analyte, mostly a chemical species out there in the ocean, dissolved maybe or in some small particulate form. And this analyte, we want that analyte and not other analytes, but that specific analyte to interact with our detector. And then the detector can work with different means, such as optics or chemistry or another physical concept. But no matter what, the analyte interacts with the detector, and the detector sends a signal. And then the signal is transduced to an electrical signal. Then it's then converted to the output that we see in our computers. So we have basically reviewed how a simple measurement works. We want simple, accurate measurements, precise measurements, also in a format that can be detected in the vast, complex matrix called the ocean water or seawater. So all these components actually require a certain degree of technological readiness. So altogether, actually, we can assign a technology readiness to our sensors. And here I'd like to review now for you. You may be finding different versions out there, but more or less that's the accepted steps in technology readiness. So usually the TRL, technology readiness TRL1, is when you have basic principles of technology observed and reported. Basic science, basically, it's done. When you actually formulate a concept or you design an application, then it's technology readiness level 2. When you actually validate, show that your concept works in a laboratory setting, in a very pilot study, then it's TRL 3. Then imagine you start taking your prototype out there in the real aquatic environment or marine environment. Then you start testing it. Then it's TRL 4. Once you validate your prototype in the example environment, when actually you further test it, you further demonstrate its utility with different texts, and it becomes TRL 5. Then when you really think that it's a prototype working in the relevant environment at a certain time frame, then it's TRL 6. Then TRL 6, beyond TRL 6, it's about your sensor being operational. Operational meaning also user friendliness, data outputs, how data are processed, how are the data or the results are integrated into other components of the observing system. So with all these steps achieved, then you start moving up in the TRL ladder, 7, 8, and 9. 9 means basically NASA terminology. It's flight ready, it can fly to space. In oceanography setting, then it means that TRL 9 is something you can leave out there, and it works, at least reliably works, for at least a year or two. So you can gather data for a few seasons. So, and we have very few TRL 9 technologies actually in ocean water. Maybe only temperature and maybe salinity CTD sensors are TRL 9. Maybe oxygen probes are approaching TRL 8 or 9, but the rest of the, especially chemical and biodiversity parameters, they are well below TRL 8. They range from all the way from TRL 3 to TRL 6. Here you see some example of different sensors out there. Salinity, water velocity, bathymetric sensors. Of course, things can be detected physically, such as bathymetry, which can be measured with the sonar technology. They are relatively mature, and they are already TRL 9. Some optical sensors are also very high maturity, TRL 9. But when you come to different analyzers, such as inorganic chemistry, then the readiness decreases. In organic chemistry, in organic molecules, the TRL readiness still not very low. Gases also, we don't have many sensors, major sensors out there. When you think about your deployment and how you want to approach to in situ sensing, we have discussed a variety of properties, detection limits, technology readiness, etc. Another thing you should consider is power consumption, because it's very hard to power up a offshore marine observatory. So you need to be thinking about different power consumption options. And usually, especially chemical sensors, they consume a lot of power. And here you see in watts, in milliwatts, different power consumption parameters of different sensors. And of course, the sensors will have different power requirements when they are in sleep mode, when they are in standby mode, and when they are continuously measuring. So you need to be also adapting your measurement frequency based on the process you are aiming. Of course, in an ideal world, you want a sensor which is adapting to changing conditions, maybe becoming very actively measuring in an episodic event, but when there are no events, maybe it's going into a sort of standby mode or low frequency measurement mode. But we are still not there in terms of sensor frequency adjustment. Usually we set a certain time frame, a certain frequency, and then that's how they do their measurements. I'd like to feature some different technologies now, and although it's about marine sensors, this course is about marine technology. Some of the technologies are also shared by atmospheric monitoring. For example, CO2 exchanges between soils and atmosphere is measured by a technology called eddy covariance. So these are a photo of an eddy covariance tower. Basically, the idea is that CO2 in the air is measured at a very high frequency, at a level very close to the soil atmosphere interface, and then basically using a statistical approach that is used, you can process different data sets, these high frequency data sets, to come up with CO2 fluxes. So same actually technology has been also adapted to deep sea oxygen and CO2 fluxes, which is basically working with exactly the same principle, very high frequency measurements with CO2 and oxygen sensors. They're coupled to also a acoustic Doppler velocimeter. So you try to correlate concentrations with vertical water movements to come up with the vertical flux. Again, the approach is statistical, but the combination of here you see three different sensors, two chemical sensors and one physical sensor, to be able to come up these sort of fluxes. I think the message here is that it's relatively maybe easy to think about measuring a concentration in the marine environment, but most of the models or different processes, you need to have rate information, you need to have information about fluxes and exchanges, and to come up with this sort of information, you need to combine different sensors. Here are more example technologies from deep sea. You can, for example, utilize colorimetry to measure different constituents. There are different electrochemical techniques such as amperometry, potentiometry, and gold amalgam voltammetry, with which you can actually characterize a variety of analytes, sediments, mats or rock, water, animal interfaces, or even hydrothermal vents in the deep sea. An important parameter, especially in the context of Black Sea, is oxygen consumption, oxygen uptake. Black Sea is one of the least oxygen containing sea basins in the world. And it's important to really very well quantify oxygen dynamics in this environment. Here you see a benthic lander application of a microsensor application, with which the sensor is actually going into going across the sediment water interface. So there's a certain oxygen concentration in bottom water, which you see above, and then oxygen decreases as soon as the probe passes through this diffusive boundary layer, and levels than zero at a certain depth inside the sediment. So using the gradient, using the slope of these sort of data sets, you can actually estimate oxygen consumption rates. It's called diffusive oxygen consumption, of course, but it gives a lot of information about the general organic load of the system, the general pollution level of the system, and the rates of oxygen consumption in the seafloor, which is a very important sink of oxygen. So we have mostly talked about maybe microsensors with fine-tipped sensors using electrochemical, maybe optical technologies. But another important direction is lab-on-a-chip technology, with which imagine you can miniaturize any laboratory technique, flow technique with this approach. You can miniaturize different pipelines, analysis pipelines on very small chips, and then you can also deploy them in situ to collect data. So one of the examples in marine systems has been developed in the University of Southampton, actually National Oceanography Center, NOC Southampton, and they have been developing in situ nitrate and phosphate and also silicate sensors using lab-on-a-chip technology, and which works quite well. It's an important step forward, especially for nutrients such as nitrate and phosphate. There is no optical. There are ways, but they are not sufficient to resolve marine concentrations. So optical and electrochemical methods are there, but they are not sufficient. So you need to be able to miniaturize the wet chemistry approach to be able to accurately detect nutrients, and this technology is one example which also has been deployed in our sister project DORS in the past few years. Of course, having these chips is not enough. You need to have, in order to deliver the sample to the chip, you need to have a range of pump and valves, and you need to have additional hardware to control the system. So in the end, even if it's a chip, then these other components build on the chip, and then still you have a very small system in situ analyzer, but the whole thing is still at a certain size. So where do we go from here? I think the next question is how these different technologies and these different tools can be combined on different platforms. So an emerging platform in oceanography is now gliders. And gliders, they typically have a certain payload. Payload meaning it's basically empty space with which can be filled with different analyzers or samplers of interest. So these sort of platforms, they do have a certain payload. Of course, the smaller the sensor is, the more lightweight your sensor is, then you can include more payload to the platform. You can include different sensors. You can then collect more data with one deployment, which is also expensive. But that's the idea. That's why miniaturization is also key in having operational oceanographic measurements. So another important platform, emerging platform, is Argo or Apex floats. So gliders are more autonomous and robotic devices. They literally glide in the ocean interior, and that's how they collect data. They can also go up and down. They can do this mooring operation. They have more versatility in terms of autonomy and navigation. But Argo floats, they are floats. So they float with currents. The only thing they can do is they can go up and down using ballast tanks, but they're also autonomous, but they are different from gliders. But they can be more long-lasting, and especially since they float with the ocean currents, it's also possible to track currents and then gather long-term information. So, but again, a float, it has a certain size, certain volume, and in order to have more sensors on these sort of platforms, you need to have also smaller sensors. So it's a very actually difficult and challenging research direction, having first, as we discussed in the beginning of this course, having first reliable sensors with low detection limits, with high technological readiness, with good integration to other systems. And then you need smaller size you need a good sampling frequency or measurement frequency. And once these platforms are equipped with these sort of tools, then the next challenge is, of course, how these platforms will work together to collect a holistic data set from the ocean. So here we are talking about ships, moored buoys, gliders, cargo floats, benthic landers. All these tools will be equipped with different sensors one day, and they will be working together. So this is where actually we will be using AI technology or Internet of Things technology, which you will be hearing also in other modules of this course. But that's the direction at least we are taking, and that's actually what our project tried to contribute as well. Here you see more information on Argo platforms. You can browse them in the slides and the additional notes and reading material that accompanies this massive online course. Another important technology is benthic observatories. Here you see a demonstration of a benthic lander. They are also autonomous, but they are deployed from a vessel, and they can stay there for a few days, and then they collect data, important data on fluxes and exchanges between the seafloor and the deep ocean. So benthic landers and also ROVs, they are important deep sea technologies, and they all one day they will be all talking to each other, hopefully, and then they will be working all together to help us monitor the oceans effectively. So let's say a little bit in the final part of my presentation, let me a little bit focus on the different specific technologies we worked in the context of Breach Black Sea project. Black Sea, as I said before, it's the largest oxygen-free and hydrogen sulfide containing sea basin in the world. Here you see a depiction taken from the MBLAS project, MBLAS Plus project, funded by UNDP. There's a certain upper layer which contains oxygen. There's doming behavior. It's a little bit exaggerated here, but just to show you, due to circulation of Black Sea, the oxygen layer is a little bit thicker towards the coasts, but it's very thin as you come to the middle of the basin. Actually, in our project, we found that the sulfidic layer in the open parts of the sea, they approach as high as 80 meters. But in the past, there were some instances that this layer rose to even 50 to 60 meters depth. So that's quite actually, considering that Black Sea is more than 2,000 deep, you can imagine that more than 90% even of the sea is oxygen free. Here you see some of the results that we generated in the project. We have been monitoring with expeditions, ship-based expeditions, temperature, density, and oxygen content of the sea. So anoxic conditions still prevails in the Black Sea, although we did not find a big shift to new creation of new anoxic zones. It looks like the situation is relatively stable. And in another module of this course, you will be hearing more about the stability and resilience of Black Sea ecosystems. Just to show you a photo, there are always people behind in the science or in the slides you see or in a figure you see. And here we are really happy that we worked with 6 countries in the Black Sea, worked together in these basin-wide expeditions. We gave access to young scientists in the frame of the project. We did sometime we met in the open ocean. We compared our results. So we co-developed, we co-designed and co-developed these expeditions, and these expeditions also served a great testing ground for the different technologies produced in the project. Here you see what we have worked on throughout the project. On the left, you see a group of smart monitoring systems and platforms we have worked on, such as glider, scamfish, benthic observatories, eDNA metabarcoding, and enzyme metagenomics. So these are more like monitoring approaches. Let's say they are not a specific technology, but they are adaptation of monitoring approaches to specific Black Sea conditions. And on the right here, we list different new sensors and tools that either we have developed or we have increased the readiness of deployment for specific for Black Sea. such as underwater unmanned aerial vehicles for jellyfish monitoring, acoustic jellyfish detectors, PCO2 detection, pH sensing, acoustic marine mammal observing, creating a digital library for phytoplankton, electrochemical hydrogen sulfide sensor, and radionuclide detector. So these different technologies have been developed for the Black Sea, or their application have been developed in the Black Sea. So they have increased in maturity to be able to maybe become operational in the near future. Here, I'd like to, for example, demonstrate one such technology. This is an electrochemical sensor where hydrogen sulfide, as I said, Black Sea is the largest hydrogen sulfide containing basin in the world. And this is how its in situ detection is being done through electrochemical sensing via a technique called cyclic voltammetry. The big peaks you see here is larger the peak is, the more hydrogen sulfide there is. So with the specific detector, for example, we have in the western basin, we have found that hydrogen sulfide started as deep as 109 meters, then increased all the way down to 254 meters. So that's actually one example of successful validation and demonstration, which enabled us to actually move up the TRL level of the sensor by a few steps. Another first in the Bridge Black Sea project was the glider deployment. So it was the first glider deployment in the Turkish economic zone in southern, southwestern Black Sea. Here you see the track of the glider and the density and dissolved oxygen data resulting from the glider deployment. This is equivalent of hundreds of basically profiles, so 376 profiles in to be specific. And each of these profiles, you get information on CTD, oxygen, chlorophyll turbidity, and nitrate, which is a big plus in a typical expedition with ship. Doing that many profiles will take maybe months of shipboard work. So these platforms will be very much important integral nature of future Black Sea monitoring, and we have also successfully demonstrated its utility. We have even found some new oxygen intrusions coming from the Mediterranean from these deployments. So we have new actual results. So these sort of deployments, not only contribute to operation monitoring, but they also open new exploration pathways. Biodiversity monitoring is, you will be hearing about that more in the part B of this module, in the smart monitoring module, but just to briefly go over, eDNA metabarcoding was developed. It's a fast and smart way of detecting which species there are in the system. We have also done extensive metagenomics, whole genome metagenomic profiling to survey for useful biomolecules that can be converted into future industrial products. So we have assessed our technologies, how mature they are after the project. The smart monitoring systems, we believe, especially our benthic observing systems and scanfish and glider work, they are now very high maturity that can be deployed in the Black Sea. The eDNA and the biodiversity method, they need more work, of course, but they have come also a long way. And for the specific tools and technologies we were able to assign at technological readiness levels to those, and especially for in situ pH and PCO2, we believe we have reached a very high level. But for some technologies such as sulfide, we have moved them at least 2 steps forward. And some other technologies such as radionuclide detector and underwater vehicles for jellyfish, for example, they have moved up by 4 technology readiness level, which was a lot of work, but it also reflects the amount of work that is done in the project. So what's next from this? Again, other modules will be touching on blue economy and how ideas and these sort of prototypes, they can be turned into proof of businesses, and how they can altogether accelerate blue economy development in the Black Sea. But basically, of course, there's a long way to go, and the whole process requires additional players, or a whole ecosystem of innovators and support mechanisms. And here we are demonstrating them as well. So developing a certain technology, showing that it works is not enough. You need to find customers, you need to find users, you need to have funding, continuous funding. You need to resolve, clarify and resolve IPR, intellectual property rights issues. In a way, you need to move towards technological readiness to business readiness. So that's how acceleration works. So with this, let me stop here. I tried to give the idea that ocean observations need to address also the three-dimensional nature of the seas, and that's where sensors, in situ technologies, smart monitoring comes into the game. This is even required. The requirement is higher from this perspective for the vertically stratified zonated Black Sea. So a variety of technologies are reaching maturity, but more work is needed, especially on chemical sensors and biodiversity technologies. But we have come a long way in the Breach Black Sea project, and we have advanced key sensing technologies for these topics. And hopefully, you will be also from other modules, you will be hearing more about how these technologies can be turned into blue economy pathways. With this, thank you, and thank you for listening and for your attention. The slides are in our massive online course system, and we are also sharing with you additional reading materials, additional links or book suggestions. So please browse and study those material for learning more on the subject, and you can always also contact us to ask for more material. Thank you.